the introduction. So today I'd like to start with a question. I know it's the afternoon. I want to get everybody woken up a little bit. So I'd like to ask you, how would you determine the composition of a truly unknown sample with GC? So if I gave you this GC sample vial, and I didn't tell you what's in it, probably compounds maybe you've seen before, but still, like, could be thousands of different compounds. What would you do to figure out what's in it and how much of each component are in it? So I'd like to see some hands and see some responses. What do you guys think? You're all chromatographers, so I know somebody knows the answer to this question.
We all know.
Yeah.
It's spiked with internal standards and run by GCMS.
Okay, GCMS, and you'd find out all of the different components in the sample, okay? What would you do next? So if I asked you how much of each component in there, what would be the next step?
We use the internal standards to do an estimate.
Okay, so how would you know the calibration factors between each of the different compounds?
Don't know the calibration.
Okay, so you just approximate it with a mass spec. Okay, so one solution. Any other approaches that people would take? Has anyone used the calibration standard? Nobody? Has anyone purchased a calibration standard and then run that on the system? So there's a number of different approaches people might take to do this, and the list I came up with was the same starting point that you came up with. The first would be identify the components with a mass spec. Maybe the next step would then just be approximating the concentrations, but if you wanted accurate results, the second step might be to purchase the calibration standards, if they're available. If they're not, then you might just have to rely on approximating the results. The next step would then be to prepare the calibration standards and run the calibration standards, create your calibration curves, which a lot of people do. And then finally, quantify the sample with those calibration results. And you might do that on the mass spec, or at this point, maybe since you've already bought the standards, you might just do it on an FID system, or something like that. So the issues that I see with these things, and the pain points, are that the standards can be costly, if they're available, that is. And then, of course, it takes time to get the standards after you've ordered them. The preparation of calibration standards can introduce error steps. So if you prepare them incorrectly with the wrong concentrations, if you don't buy them from a reputable source, and then running the calibration standards is time-consuming, because you might do a 5-point calibration curve and look at repeats for each of those samples, which can lead to time. It might be one day a week, it might be one day a month. And then finally, you have to quantify using those calibration results. So my question, and the rest of this talk, is about whether or not there's a system that can eliminate these steps and allow you to get an answer more quickly by saving money and do it with less potential error. So, the answer is yes, of course, because if it was no, then the talk would be over. So the solution that we propose here to be able to do this is using simultaneous compound identification and quantification. So using a GCMS to figure out what's in the sample, using existing libraries, or the other proposed solution could be using a software or a mass spec that could accurately give you an accurate mass, so you can get the molecular formula and the number of carbon atoms. And then using quantification with a microreactor that converts all components to the same species. And Paul talked about that, so I don't need to go in detail about the reactor. So in specific, the configuration that we've developed to be able to do this is shown here. So it's a typical GC on the front end, consisting of an inlet and a column. But then after the column is where you perform a split, so you can do simultaneous quantification and identification. So the splitter that we're using is a CFT splitter, which is a capillary flow technology. And really all it is it's a device, it's just a union. It's really just a 4-way union that's coated with an inert coating to prevent molecules from sticking. The reason why there's 4 connections on here is for an aux pressure controller to control the pressure of the splitter. And I'll get into why that's important in the next slide. The splitter then is connected to a mass spectrometer through a retention gap, and in this case the Polyarc through another retention gap. And everything that reacts in the Polyarc then goes and is detected by the FID. So the keys here and the difficult points that we had to figure out before this would work was maintaining a constant split ratio as a function of oven temperature. Because if the split ratio changes as a function of oven temperature, and you have a single standard in your chromatogram or you're using an external standard, well then you can't relate the area per mole of carbon, for example, of that standard to all the rest of the peaks. So you have to have a constant split ratio when the oven temperature changes. And you don't want to be just limited to isothermal methods because that would limit you to a very small subset of analyses. And the second is the equimolar carbon response for all compounds. And we've already achieved that with the Polyarc because it converts everything into methane. So getting into a little bit about the theory behind these splitters. So this is just a schematic of what's happening with the split. So you have an inlet and then a column that goes to the splitter, and then the splitter goes through the mass spec in the Polyarc with two capillary restrictors. And the flow in both of the capillary restrictors is governed by Pucell's equation for compressible fluids. And this is the same equation that all the GC manufacturers implements into their software to calculate the flow through the column. So the ratio of the flow that goes to the mass spec versus the Polyarc is just dependent on the parameters shown here. So it's dependent on the viscosity of the gas, so it might be helium or it might be hydrogen. It's dependent on the radius of the restrictor, the length of the restrictor. The temperature is usually referenced to a temperature that makes sense, so usually it's STP where people reference these flows, and so that's shown in the equation here. And then it's dependent on the pressure drop, and that's really the key parameter that governs the split ratio in a splitter is the pressure drop between the pressure at the splitter and the pressure of the device. So for a mass spec, that's zero of an absolute pressure, and at the exit of the Polyarc is ultimately atmospheric pressure. So in order to keep a constant split ratio, you have to keep a constant pressure difference between the splitter and the detectors, which is this term here. And the problem is that if you don't use a pressurized splitter with an added flow, what will happen is you increase the oven temperature, the viscosity of the carrier gas increases, and that changes the ratio of the flow rates of the two devices. And then that won't allow you to keep that constant split ratio and get accurate results. So the key is to add an aux pressure. And so that was the EPC that I showed on the previous diagram, which is a pressure controller that adds helium to the splitter. It actually adds more helium at room temperature and adds less and less as it gets hotter and hotter to maintain a constant pressure at the splitter. And now that you have a constant pressure, the pressure difference between the splitter and the detectors is maintained. The one exception to that is that the Polyarc, the back pressure actually changes slightly with oven temperature. So there's a couple of ways to get around that. Either programming the pressure, if you're interested in having a large split ratio to the mass spec, then you can program that pressure to change with oven temperature. Or if it's okay, sending about 10% to the mass spec and 90% to the Polyarc, which is okay for most people, and it doesn't decrease the sensitivity much of the mass spec. This problem is minimal and is less than a couple of percent over the entire range, so you can still get accurate results, keeping a constant pressure at the splitter. So we tested this in our laboratory by doing a series of experiments where we looked at changing the splitter pressure with time as the oven temperature changed. So we concomitantly changed the splitter pressure to match the oven program, and we checked the split area for each of these experiments. And this really confirmed what we had learned from the theory of doing the split, to determine that when we keep a constant split pressure, we get just a very small area of about 1 to 2%. And if we program the split pressure, we can get the error down to just above or just below 0.5%. So both methods work pretty well for keeping a constant split ratio versus temperature. So that figuring out this theory has allowed us to be able to keep this constant, which that enable us to get accurate results. So coming back now, and then to our sample. So our data now is we're getting simultaneous data from both the mass spec and the FID. So this is just one example of an E85 gasoline sample where you see very similar signals between the Polyarc and the mass spec, where on the mass spec signal you're able to identify each of the components, and on the FID signal is where you get your quantitative information and you use that to obtain your results. So the way in which you quantify with a device that gives you an equimolar carbon response is using this equation here, which is sort of the governing equation for the Polyarc. The concentration of any component of interest can be calculated from the concentration of a single internal standard added to the solution, along with the ratio of the areas, and then the ratios of the molecular weights and the number of carbon atoms is what converts a moles of carbon percentage into a mass percentage, because most people quantify in terms of mass. If you're quantifying in terms of moles, you can get rid of the molecular weight component, and if you're just quantifying on a carbon basis, maybe as a reaction product, you can get rid of both of these terms. But here with the mass spec split is where you figure out these two terms. So you get the ratio of areas from the Polyarc data, and you get the molecular weight and the number of carbon atoms of your analyte from the mass spec data, and now you're able to determine the concentration of any analyte with a single internal standard without having to calibrate for that analyte. So now getting back to that original sample we had. So the best way, or one way to do these analyses is to take a sample, an unknown sample, and add an internal standard of a known concentration. Now you know the concentration of that internal standard. You run a single injection with the GC Polyarc mass spec, and you get a chromatogram. This is the Polyarc chromatogram, but you'd also get the mass spec chromatogram. You go through and identify each of your components, and then determine the molecular weight and the number of carbon atoms of each of those components, and now you're able to quantify for each component in the sample. So this is a paint sample with a number of solvents in it, and in fact this is just a fraction of the components. This is just 5 of the components. But for samples that have a lot of components where it's time consuming to go through and calibrate each component, I think that's where this is most useful. Another example shown here is crude isoprene. This is a C5 fraction that comes from a catalytic cracker, where you have 10 to 20 components, and it's a very similar approach. There's many ways to quantify. In this example, I didn't even add an internal standard because I referenced everything to the total concentration of hydrocarbons in the sample. So people quantify in different ways, either adding an internal standard or sometimes just quantifying based on every GC peak you see, and that's what we did here for isoprene. And here you can see 20 components, which again we just quantified with a single injection. Another example, something that we did just recently, and this was done with Gregory Janis at MedTox, was we looked at ethanol and blood using this method with the GCMS, where we took the same approach and we took our sample with an unknown concentration of ethanol. We added a 1-propanol internal standard, and then measured the Polyarc and the mass spec signals so we could identify and quantify. This chromatogram actually shows a standard, a serum standard that contains other components other than ethanol, such as acetone, propanol, methanol. And then in the Polyarc signal, you also see CO2, which is also converted to methane. So, the list sort of goes on about all the different, applications that you could potentially apply this to. But for ethanol and blood, we did a calibration-free method where we looked at, whole blood, urine samples, serum samples, and found that using this calibration-free method, the actual ethanol concentration matched quite well in a parity plot over a large range of concentrations. So one final example they'll show here is FAMES. This is a mixture of fatty acid methyl esters where we did the same thing. We injected this in the GCMS and identified all the compounds from C6 to C24, and then quantified them again in the same injection. And we saw less than 2% average error over the entire range, which is which is a wide range in boiling points and molecular weights for these compounds. So, you know, I've just shown you a few examples where this sort of thing can be useful, but anywhere where you've got a compound that's unknown, that you'd like to determine what it is and how much it is and how much there is in there, can all be done in a single injection, and 2 injections if you just want to make sure the first one, you know, you're getting reliable results. So I've just shown you a few examples of that here in this presentation. But really what it comes down to is, you know, comparing the old method, which can be 5 steps, or maybe less steps if you're willing to, you know, approximate the calibration factors, and then reducing that down to 1 step, which comes back to, you know, the time savings, and then, you know, saving money and reducing those error-prone steps. So ultimately, we made you know, a system which can do this mass spec split, which is, you know, one method of doing this, and it'd be great to get your feedback about what you think and potential application for it. Thank you.